Last time we proved the fundamental theorem of Riemannian geometry, which says that there exists a unique connection nabla in the tangent bundle Tm, which is compatible with the metric and is symmetric. I want to present very briefly two examples. The first one is provided by the Euclidean connection, the Levi-Civita connection on a Euclidean space coincides with the Euclidean connection nabla bar. This result follows immediately from the fact that nabla bar is compatible with the metric. It is also symmetric, and we know that the Levi-Civita connection is unique. So nabla bar must coincide with this connection here. Second example, suppose that M is an embedded submanifold of a Euclidean space then the Levi-Civita connection on M coincides with the tangential connection denoted by this symbol. The strategy for proving this statement is the same as the one we used for proving statement number 1, because we have to use the fact that this connection is compatible with the metric, and it is symmetric. And I hope that you solved this, proved this statement as an exercise. I mentioned this, I think, in the past. And use again the fact that the Levi-Civita connection is unique. So this connection and must coincide with the Levi-Civita connection. What I want to do now is to show one consequence of the fact that the Levi-Civita connection are defined in a way which is independent from the coordinates. Precisely, I'm sure you remember the formula which says nabla x y inner product z. This can be written as 1/2 multiplied a formula which involves only operations between vector fields, and it does not involve the local coordinates that we are using. A consequence of this fact is what we call naturality of the Levi-Civita connection. Roughly speaking, this means that the Levi-Civita connections behaves well under the action of isometries. What does it mean? If nabla is the Levi-Civita connection of the manifold Mg, and nabla tilde is the Levi-Civita connection of M tilde G tilde, where we assume that Mg and M tilde G tilde are Riemannian manifolds with or without boundary. Then if phi from M to M tilde is an isometry, then the pullback of nabla tilde must coincide with nabla. I want to prove this result. In order to do this, I want to recall the definition of this connection. So phi star nabla tilde of y along x, this is defined as a phi inverse star of phi star y. Okay, let's prove that this identity holds true. Since the Levi-Civita connection is unique, we have only to prove that phi star nabla tilde is compatible with the metric and is symmetric. We use, of course, the fact that phi is an isometry, and it is useful to remember what being an isometry means. So x, y in Tm and p in M, then if phi is an isometry, then I have that xp yp coincide with d phi p yp d phi p. Sorry, I made a typo. I made a typo because I have to work with y and z and not with x and y. And I can write down this number as phi star y evaluated at phi p inner product phi star z evaluated at phi p, and if we drop the index p, which is the point of the manifold, we can do this because p is arbitrary. Then we can write yz equal phi star y phi star z composed with phi. To prove that phi star nabla tilde is compatible with G means that if x, y, z are in Q of M, then x applied to this function, this is equal to phi star nabla tilde of y along x z plus y phi star nabla tilde of z along x. So we have to prove that this identity holds true. Let's start from here. This is equal to x acting on this function here. So I will write just phi star y phi star z composed with phi. But so here you have that x is acting on the composition of two functions. Consequently, you can write this as phi star x acting on phi star y phi star z composed with phi. But this is equal to precisely what you have into this bracket. This can be written as nabla tilde phi star x of phi star y phi star z plus phi star y nabla tilde phi star x of phi star z. I don't like what I wrote, so I will rewrite better. And this follows from the fact that phi star, that nabla tilde is compatible with the metric. Essentially, I am using no, maybe it's more confusing if I tell you more. It's enough to say that nabla tilde is compatible with the metric because this is a Levi-Civita connection. Then this is equal to phi inverse star nabla tilde phi star x of phi star y z plus y phi inverse star nabla tilde phi star x phi star z. And this follows, this identity follows from the definition of isometry. Essentially, if you look at this formula, here you have the inner product of two vector fields, which is equal to the inner product of the push forward of the same vector fields composed with phi. How can you use this formula to get that this is equal to this? Here you have that there is this inner product here composed with phi, and you want to use this formula where instead of phi star y you have this, and phi star z appears in both formula. Then you want to write this in this form. To pass from here to here, you can compose this vector field with the inverse of this map. This is why there is this map here, this symbol here. And you replace phi star z by z. This is why you have z here. And same technique for proving that this term composed with phi is equal to this. Here I am using this formula where instead of phi star z you have nabla tilde phi star x applied on phi star z. You compose with phi inverse star, you apply phi inverse star, and you get that phi star y is replaced by y, phi star y is replaced by y, and instead of nabla tilde blah blah blah, you have phi inverse star, the same object. And this is equal to phi star nabla tilde of y along x plus y phi star nabla tilde of z along x. And this follows from the definition of pullback connection, and this is exactly the right hand side of this identity. So we prove that x acting on the inner product of y and z is equal to this sum here. So we proved that we have the compatibility with the metric. So now we should prove the symmetry. So we have to prove that phi star nabla tilde of y along x minus phi star nabla tilde of x along y, this is equal to the Lie bracket of x and y. But the left hand side is equal to phi inverse star nabla tilde phi star x phi star y minus nabla tilde phi star y phi star x. This identity is true because of the definition of phi star nabla tilde. You get that this is equal to phi inverse star acting on this term, and this one is equal to phi inverse star acting on this object. But what is this? This is the Lie bracket of phi star x and phi star y. And if you expand, you will get that this is xy. I leave as an exercise the proof of this corollary, which says that geodesics behave well under the action of isometries if gamma is a geodesic in Mg, then phi composed with gamma is a geodesic in M tilde G tilde. The next topic of today is the exponential map. The our goal is to understand how geodesic change if we change the initial point or the initial velocity vector. The dependence of geodesics on the initial data is encoded in a map known as exponential map, and this is defined on the tangent bundle to the manifold with values in the manifold. I need a preliminary lemma known as a rescaling lemma, which says that if P is a point in M, V is a point in TPM, that is, it is a tangent vector, C, T are real numbers, then you have this identity. Whenever either side is defined I'm sure you remember what I mean by gamma v. Gamma v is the geodesic having initial velocity vector equal to v, and the initial point given by the image by v of the projection pi. So gamma v at 0 is pi v equal p. Instead, gamma cv is the geodesic having as initial velocity vector the vector cv. Okay, let's prove this because it is interesting. So if c is equal to 0, there is nothing to prove, because gamma 0 t this is equal to p. Why this is true? It is true because gamma 0 is a geodesic having initial velocity vector 0, and we know that if we work with the Levi-Civita connection, the length of this vector here is constant. So by assumption, this is 0, implies that this is always 0, and this is equivalent to say that this is 0. This means that gamma is a constant geodesic having value p. Instead, what is gamma v0? It is p by definition. So there is nothing to prove. So we can assume that c is different from 0. We have to show that gamma cvt exists, and star holds true whenever the right hand side is defined. Why? Because the substitution v equal c prime v prime, t equal c prime t prime with c prime equal 1 allows me to convert the right hand side of this equation into the left hand side, and vice versa. Precisely, gamma cvt becomes gamma c prime v prime c prime t prime equal gamma v prime c prime t prime, and the gamma v ct changes into gamma c prime v prime c prime t prime equal gamma c prime v prime t prime. So if I prove that this is equal to this when the right hand side is defined, then I have also proved that this is equal to this when the left hand side is defined. Suppose that I is the maximal domain of definition of gamma V, and we define gamma tilde from C inverse I in M, writing gamma tilde T equal gamma Ct, where I dropped the V from the notation. So let's use just gamma, where C inverse I is the set of points of the form C inverse T with T in I. I have to prove that gamma tilde 0 is P, gamma tilde prime 0 is CV, and it is a geodesic. Then by the property of uniqueness and maximality, this curve must coincide with gamma CV, which means that gamma CV exists. And it also says that the formula star holds true. Okay, so gamma tilde 0 is gamma 0 equal P. So now we have to compute gamma tilde prime 0. Suppose that gamma t in local coordinates is gamma 1t, gamma n t. Then what is gamma tilde I dot? This is ddt of gamma I ct, that is c gamma dot I evaluated at ct, and this implies that gamma tilde prime 0 is given by C multiplied gamma dot 1 0 gamma dot n 0, that is C times V. So now it remains to prove that it is a geodesic, and then we will have finished. So gamma tilde is a geodesic if dt tilde gamma tilde prime t is identical to 0. Here dt tilde is the covariant derivative along gamma tilde. So this is ddt of gamma tilde dot k plus gamma tilde dot it, gamma tilde dot jt, gamma ijk, gamma tilde t. So this is just the definition of dt tilde gamma tilde prime t. Now we use this formula. Observe that we have to derive with respect to t gamma tilde dot k. So we have a constant c coming out this formula, and a second constant c coming from the derivative with respect to t. So I can write c squared gamma second k ct plus I have gamma tilde dot I is on the blackboard, so I have c. A second constant c comes from gamma tilde dot j, so I can write c squared gamma dot I ct gamma dot j ct gamma I j k gamma ct, and I have to multiply everything by delta k, but this is c squared times gamma dot k, gamma dot I, gamma dot j, gamma ijk, and this is nothing but t gamma prime ct. But gamma by hypothesis is a geodesic, so this is 0, and c squared times 0 is 0. So gamma tilde is a geodesic, and gamma tilde coincides with gamma cv, and it is the end of the proof. Now we are ready to define the exponential map. We define E equal V in Tm such that gamma V is defined on an interval containing 0, 1, then we can define the exponential map exp from E into M, writing exp V equal gamma V1. The reason why this interval must be contained in the interval of definition of gamma V is that we are evaluating gamma V at t equal 1. Then if P is a point of M, we can define the restricted exponential map at P, denoted by this symbol as exp restricted to EP, where EP is E intersection TPM. Okay, let's see what are the properties of the exponential map. A, E is contained in Tm and it is open. And EP, E contains the image of the zero section, and EP is star shaped with respect to 0. A set is star shaped with respect to 0 if for each point x in that set, then the line segment joining x to 0 is contained in that set. B, for each V in Tm, gamma V is given by gamma Vt equal exp Tv for all t such that either side is defined. C, exp is smooth. D, for each P in M, the differential of exp p, the restricted exponential map at 0 from T0 TPM into TPM is the identity map of TPM. Let's try to prove this. We will start proving B first. We use the rescaling lemma that is gamma CVT equal gamma VCT with t equal 1, and we get that gamma CV1 is gamma VC. But gamma CV1 is exactly exp CV, and we prove that exp CV is gamma VC, and up to a change of notation we have this identity. If V belongs to EP, that is E intersection TPM, then by definition gamma V is defined on some interval, let's say I, containing at least 0, 1, so if t belongs to 0, 1, this lemma here implies that gamma TV1 is gamma VT, but this is exp TV is defined. If this is defined, for t in 0, 1, this means that the line segment joining V to 0 is contained in EP. This says that EP is star-shaped. with respect to 0. The difficult part of the proof is the one which allows us to prove that E is open and the exp is smooth. Suppose that Ux1 xn is a local chart for M, and suppose that V in TPM with P in U is written this way: VI ddx I at P. Then you know that pi inverse U x1 xn v1 vn is a chart, local chart in Tm, where pi is a projection from Tm to M. When we prove the existence and uniqueness and smoothness, I think, sorry, existence and uniqueness, I made a mistake, uniqueness, of geodesics, we have seen that the geodesic equation is equivalent to solve the following problem: determine the integral curve eta t x1t xnt v1t vnt of the smooth vector field G, known as geodesic vector field, whose formula is this: gxv equal vk ddxk at xv minus vi vj gamma ij kx d dvk at xv And I think it's clear that every geodesic, every integral curve of G gives you a geodesic by projection. That is using pi from Tm into M. Roughly speaking, this means that if eta t is an integral curve of G, then the geodesic you want is just the curve parameterized by x1t, x2t, xnt. So this means you compose eta t with pi. G has this property, which is very important. G defines a global vector field on Tm. This is apparently not clear. The reason of this is that the formula for G is local, because we are using the coordinates. But if we are able to prove this, then we can use the fundamental theorem on flows. So first, let's prove that this is true. In order to prove that this is true, it is enough to show that if f is in C infinity Tm, then GF PV, this is ddt, t equals 0, f gamma vt, gamma v prime t. This is what we want to prove. If this is true, this is true. Why? Because this formula is independent from the coordinates, and these define the action of G on functions, and this means is a vector field. Sorry for the typo. And this vector field is global because I'm not using coordinates. To prove that this is true, we look at the right hand side, and we use the chain rule and the geodesic equation. So what is this? This is d dx k of f evaluated at xt vt. This is true because the parameterization of gamma v is x1, x2, x3, xt, and the parameterization of gamma v prime t is given by vt. The reason why this is true is that to define the vector field G, we used this substitution. Vk t equal x, let's use the notation dot k t. Consequently, Vt, whose component functions are v1t, v2t, vnt, is the parameterization of gamma v prime. Times x dot kt plus df dvk xt vt v dot k t at t equals 0. This is equal to df dxk at pv. If I write t equals 0, then I will get x0, which is p, and v at 0, which is v. That is the initial velocity vector of this geodesic. Now I use the substitution I erased. This is v k at 0, that is vk, plus df dvk pv, and for this I use the geodesic equation, and I get minus vi at 0, vj at 0, gamma I j k at gamma v0 I need one. Okay, so this term here is just minus df dvk pv vi vj gamma I j k p. But do you remember the formula I wrote down for G? This is exactly G acting on F. So this is true. Now I have a global vector field on Tm, so I can use the fundamental theorem on flows, and this implies that there exists a smooth map theta from D into Tm, where D is some open set in R times Tm, such that theta t at PV, that is denoted by theta PVT is the unique maximum integral curve of G starting at PV. And the theorem says also that D contains 0 times Tm. This means that this curve is defined on an interval containing 0. Remember that we want to prove that E is open. How to prove this? So suppose that PV is in E. Then this means that I have that the geodesic gamma V is defined on an interval, at least on an interval containing 0, 1, and I get that the same property holds true for the integral curve of G starting at PV. This means that 1 PV belongs to D, where D is this set. But D is open, so D open implies there exists a neighborhood of 1 PV in R times Tm on which the integral curves of G are defined. In particular, this means that there exists a neighborhood of PV such that the integral curve starting at PV are defined on the interval 0, 1. But if this is true, the geodesic map, the exponential map, will be defined on a neighborhood of PV. The reason is that the integral curve of G have a projection which coincide with the geodesic curves. So this means that if the integral curve are defined on this neighborhood, then you can define the exponential map on that neighborhood. And this says that E is open because we found a neighborhood of PV on which the exponential map is defined. Next goal, exp is smooth, but this is easy. We have said that the projection of the integral curves of G are the geodesics. So gamma Vt is pi of theta t Tv. This is the integral curve of G. If you compose with pi, you get the geodesic. So gamma V1 is pi of theta 1 Tv, but this is exp V. But this is a smooth map by the fundamental theorem of the flows, and this is smooth, so exp is smooth. Implies exp smooth. And now it remains to prove that the differential of exp at 0 acting on V is V, that is differential of exp at 0 is identity. So I have to prove this. How do you prove? How do you compute the differential of function? Simple. Suppose that tau is a curve in TPM such that tau 0 is 0. This is this 0 here, and tau prime 0 is V, that is this vector here. Then this differential here, the exp p0 at V, this is d dt of exp p composed with tau at t equals 0. A curve satisfying this hypothesis is, for example, this one. So this is equal to ddt of exp p tv at t equals 0, that is ddt of gamma vt at t equals 0, that is v. We proved that this identity holds true, and this says that the differential of the exponential map at P is the identity on TPM. I think is a good point where to stop. Thank you for your attention.